Ustad Sam Rasulullah is where we left at 3 days ago. It says here. Oh my god. So long, huh? It's been. So let's start. Shapes of distribution. Okay.
So what I want to talk about now are shapes of distributions and different words we might use to describe those shapes. So right over here, let's see, we're talking about Matt's Cafe, and we have different age buckets. So this is a histogram here. And in each bucket, it tells us the number of guests that are in that age bucket. So we don't have any guests that are under the age of 20. We have a reasonable number between 20 and 30. We have a lot of guests at 30 in that bucket between 30 and 40, reasonable number between 40 and 50. And then as we get older, we have fewer and fewer guests. So just when you look at something like this, a distribution like this, something might pop out at you. It kind of looks like, if you were to imagine this were an armadillo, this would be the body of the armadillo. And then what we see to the right kind of looks like the tail of the armadillo. And we actually use those types of words to describe distributions. So this distribution right over here, it looks like it has a tail to the right. It doesn't have a tail to the left. In fact, we have no one under the age of 20. But here, when we have a few people between 60 and 70, even fewer between 70 and 80, even fewer between 80 and 90, and if it kind of keeps going like this is a tail, and it's on the right side. It's a right-tailed distribution. So I'd call this distribution right-tailed. And I'm using Khan Academy exercises because it's a good way to see a lot of examples and actions. So this distribution right over here, it looks like it has a tail to the right. Each bucket, it tells us the number of guests that are in that age bucket. So we don't have any guests that are under the age of 20. We have a reasonable number between 20 and 30. We have a lot of guests at 30 in that bucket between 30 and 40, reasonable number between 40 and 50. And then as we get older, we have fewer and fewer guests. So just when you look at something like this, a distribution like this, something might pop out at you. It kind of looks like, if you were to imagine this were an armadillo, this would be the body of the armadillo. And then what we see to the right kind of looks like the tail of the armadillo. And we actually use those types of words to describe distributions. So this distribution right over here, it looks like it has a tail to the right. It doesn't have a tail to the left. In fact, we have no one under the age of 20. But here, when we have a few people between 60 and 70, even fewer between 70 and 80, even fewer between 80 and 90, and if it kind of keeps going like this is a tail, and it's on the right side. It's a right-tailed distribution. So I'd call this distribution right-tailed. And I'm using Khan Academy exercises because it's a good way to see a lot of examples. And frankly, you should too, because it'll help you test your knowledge. But it's not left-tailed. Left-tailed, we would see a tail going like that. And frankly, if you're left-tailed and right-tailed, you're likely to be approximately symmetrical. Remember, symmetry, you define a line of symmetry, and one type of symmetry is one where if you were both sides of that line of symmetry are kind of mirror images of each other. You could fold over the line of symmetry and they'll roughly meet. And this one does not meet that, because if you were to say, hey, maybe there's a line of symmetry here, and you were trying to fold this over, it wouldn't match up. The two sides would not match up. So I feel good saying that it is right-tailed. So let's see. Retirement of age of each guest. Well, yeah, these names aren't that great, but let's actually see what they're saying. They're saying by age, they're telling us the number of guests. So this is the number of guests at a Logan assisted living. So we have a lot of guests that are between 60 and 70 years old, or reasonable that are between 50 and 60, or 70 or 80. And this distribution actually looks pretty symmetrical. If I were to draw a line of symmetry right down here, right at around an age of, I guess the line would be right at an age of 65, I guess you could say, although this is a bucket for ages 60 to 70, then you could flip it over and it looks pretty symmetrical. Not exactly. This bucket doesn't quite match up to this one, but it's pretty close. These roughly match each other. These roughly match each other. So I feel good about saying it is approximately symmetrical. Now, just to know what these other words mean, skewed to the left or skewed to the right. These actually have fairly technical definitions when you get further in statistics, but I guess easier to process version of them are when you have a left tail, you tend to be when you are left-tailed, you also tend to be skewed to the left, and when you are right-tailed, you tend to be skewed to the right. Another way to think about skewed to the left is that your mean is to the left of your median and mode. That might not make any sense to you. You might just want to go after the tail. If you're left-tailed, you're probably left skewed. If you're right-tailed, you're probably right skewed. So let's keep going. Let's see if we can see. Let's actually see another example. So this is interesting. This is not, we're not given a histogram here. We're not given a bar graph. We're given a box and whiskers plot, which is really just telling us the different quartiles. So just to remind ourselves, this tells us the minimum of our data set, the bottom of our range, so the minimum value in our data set. we have at least 111. And then the maximum value of our data set, we have at least 125. Now this line right over here is the median. The middle number is 21. And then the box defines the middle 50% of our numbers. So it's kind of the meat of our distribution. So if we were to try to visualize what this would look like as maybe a histogram, and we don't know for sure because we might have a whole bunch of 11s, not so much that it skews this, but we could have more than one. But a distribution that this could match up with is something to remind ourselves. This tells us the minimum of our data set, the bottom of our range. So the minimum value in our data set, we have at least 111. And then the maximum value of our data set, we have at least 125. Now this line right over here is the median. The middle number is 21. And then the box defines the middle 50% of our numbers. So it's kind of the meat of our distribution. So if we were to try to visualize what this would look like as maybe a histogram, and we don't know for sure because we might have a whole bunch of 11s, not so much that it skews this, but we could have more than one. But a distribution that this could match up with is something that looks like having a tail down here, and then you kind of bump up here. This is the meat of the distribution. It kind of looks something like that. And I can't draw because I'm doing this on the exercises right now. But for something like that, well, something like that would have a tail to the left. It has its range goes, fairly low to the left, but it might not have a lot of values there. If it had more values on the left side, this box would have been shifted over because a larger percentage would have been on the left, so to speak. And so this one, I feel pretty good about saying this is skewed to the left. It's definitely not symmetrical. If it was symmetrical, the median would be pretty close to the center. The box would be pretty centered. And it's not skewed to the right. If it was skewed to the right, you would have a tail to the right. You would have this whisker would likely be much, much, much longer. And we're done.
This is where it gets getting confusing. For me, at least. This interpretations of graphs, would you say? What do you call them? Anyways, skewed to the left, skewed to the left. Well, if there is a tail skewed to the left, that's obvious. But this one, check this one out. Oh my god, shapes of distribution. Oh my god, here we go. Roughly symmetric. Okay. Which of these best describe the shape of distribution? Right skewed, left skewed. Okay. I'd say this is symmetrical, huh? Am I correct? Approximately symmetric. Not symmetric when it starts. I don't know what these are. Starts with 3, ends with 19. So 3 minus 19, that's 19 minus 3, that's 16. 16 over 2, that's 8. So it should be 8. That's 8, am I correct? I don't know. I seriously don't know. 3 points, 4 points. Okay. 1, 2, 3, 4. 4 points. Approximately symmetric. Wouldn't you say? I'd go with approximately symmetric. Okay. Skewed to the left. Clusters, gaps, peaks, outliers.
In this video, I want to do some examples looking at distributions, in particular different features in distributions like clusters, gaps, and peaks. So over here, I want to do it with some examples. Which of the following are accurate descriptions of the distribution below? Select all that apply. So the first statement is the distribution has an outlier. So an outlier is a data point that's way off of where the other data points are. It's way larger or way smaller than where all of the other data points seem to be clustered. And if we look over here, we have a lot of data points between 0 and 6. And just let's think about what they're measuring. This is shelf time for each apple at Gorge's Grocer. So, for example, we see there's 1, 2, 3, 4, 5, 6, 7 apples that have a shelf life of 0 days. So they're about to go bad. You see you have 1, 2, 3, 4, 5, 6, 7, 8 apples that are going to be good for another day. You have 2 apples that are going to be good for another 6 days. And you have 1 apple that's going to be good for 10 days. And this is unusual. This is an outlier here. It has a way larger shelf life than all of the other data. So I would say this definitely does have an outlier. We just have this one data point sitting all the way to the right, way larger, way more shelf life than everything else. So it definitely has an outlier, and this one would be the outlier. The distribution has a cluster from 4 to 6 days. And we indeed do see a cluster from 4 to 6 days. A cluster, you can imagine, it's a grouping of data that's sitting there, or you have a grouping of apples that have a shelf life between 4 and 6 days, and you definitely do see that cluster there. And since I already selected 2 things, I'm definitely not going to select none of the above. So let me check my answer. Let me do a few more of these. Which of the following are accurate descriptions of the distribution below? And once again, we're going to select all that apply. So the distribution has an outlier. So let's see, this distribution, I do have a data point here that's at the high end, and I have another data point here that's at the low end, but I don't have any data points that are sitting far above or far below the bulk of the data. If I had a data point that was out here, then yeah, I would say that was an outlier to the right, or a positive outlier. If I had a data point way to the left off the screen over here, maybe that would be an outlier, but I don't really see any obvious outliers. All of the data, it's pretty clustered together. So I would not say that the distribution has an outlier. The distribution has a peak at 22 degrees. Yeah, it does indeed look like we have, and let's just look at what we're actually measuring, high temperature each day in Edgeton, Iowa in July. So it does indeed look like we have the most number of days that had a high temperature at 22, most number of days in July had a high temperature at 22 degrees Celsius. So that is a peak, and you can see it. If you imagine this is kind of a mountain, this is a peak right here. This is a high point. You have at least locally, you have the most number of days at 22 degrees Celsius. So I would say it definitely has a peak there. Since I selected something, I'm not going to select none of the above. Let's do a couple more of these. Which of the following are accurate descriptions of the distribution below? So the first one, the distribution has an outlier. So let's see, this number of guests by day at Seth's Sandwich Shop. So let's see, the lowest they have no days where he had between 0 and 19 guests. No days where he had between 20 and 39 guests. Looks like there's about 9 days where he had between 40 and 59 guests. Looks like 20 days where he had between 60 and 79 guests. All the way that it looks like this is maybe 8 days that he had between 180 and 199 guests. But in the question of outliers, there doesn't seem to be any day where he had an unusual number of guests. There's not a day that's, way out here where he had like 500 guests. So I would say this distribution does not have an outlier. The distribution has a cluster from 0 to 39 guests. So 0 to 39 guests is right over here, 0 to 39 guests. And there's no days where he had between 0 and 39 guests, either 0 to 19 or 20 to 39. So there's definitely not a cluster there. I would say that the cluster would be were days that had between 40 and 199 guests. Definitely not 0 and 39. There was no days that were between 0 and 39 guests. So I would say none of the above very confidently. Let's do one more of these. Which of the following are accurate descriptions of the distribution below? All right. The distribution has a peak from 12 to 13 points. Let me see what this is measuring, or what this data is about. Test scores by student in Miss Frine's class. So you had one student who got between a 0 and a 1 on a 20-point scale. So got between, I guess you maybe out of 20 questions, got between 0 and 1 points. And then you see that there's no students got between 2 and 3, or 4 and 5, or 6 and 7. Then we have another student who got between 8 and 9. Looks like 3 students got between 10 and 11. And then we keep increasing. This looks like it's about 12 students got either 16 or 17, or something in between, maybe if you could get decimal points on that test. And then it looks like 10 students got from 18 to 19. All right, so this says the distribution has a peak from 12 to 13 points. 12 to 13 points, there were 5 students, but this isn't a peak. If you just go to 14 to 15 points, you have more students. So this is definitely not a peak. If you were looking at this as a mountain of some kind, you definitely wouldn't describe this point as a peak. You would say this distribution has a peak, has the most number of students who got between 16 and 17 points. So that's the peak right there, not 12 to 13 points. So I would not select that first choice. The distribution has an outlier. Well, yeah, look at this. You have this outlier. Most of the students scored between 8 and 19 points. And then you have this one student who got between 0 and 1. It's really an outlier. You even see this, when you look at it visually, it's not even connected to the rest of the distribution. It's way to the left. If something's way to the left or way to the right, that's an outlier. If it's kind of unusually low or unusually high. So I would say this distribution definitely does have an outlier. And I'm not going to pick none of the above since I found a choice. And I think we're all done.
Okay. Set views. There is a data point that is very far, far from the center. I don't think so. There is a cluster from 0 to 40 gates. None of the above. Okay. There's an outlier here. Peak at 6 hours. No. There's a cluster from 7 to 9 hours. 7 to 9 hours. Yep. Okay. Yep. What do you call it? It's an outlier. There's a peak from 40 to 45. 40 to 45. There is a peak. There is a data point that no. There is a peak at 22. I would say yes. There is a cluster from 0 to 15. Yep. There's a gap from 25 to 30. Yep. There's a data point that is very far from center. Yes. There's a gap between 7 to 8. 7 to 8. Comparing distributions. notebooks. Should we say that this is enough for one day? Because we have pre-calculus. That will take time.